Now we are going to look at the discrete Fourier transform. And as I had said, this is DFT. So this has the potential to be the fifth Fourier series representation. Let us now define this, then see how it looks like, and then we will see whether it is the fifth Fourier representation that we are going to encounter. So we are given x of n over n equal to 0, 1, 2 up to cap n minus 1. So n data points are given to you. We are further told there are no assumptions made about x of n outside 0 to n minus 1. Now what do we mean by this? Suppose I give you n data points and then I tell you there are no assumptions about x of n outside these values. If you want to make an assumption about x of n outside 0 to n minus 1, one natural assumption that will come to your mind would be 0, alright. So it is in that context what we are saying is no assumption is made about x of n outside 0 to n minus 1, and then somebody comes along and says, okay, you want the DFT, here is the DFT, right, almost God given, right. This is the DFT, take it, do not argue with me, right. So x of k is defined like this. N going from 0 to cap n minus 1, x of n e to the minus j 2 pi k n by cap n. This is the definition, okay. And now if you look at this, immediately you can realize x of k plus cap n, wherever little k is there, if you replace little k by k plus cap n, what happens, right. So here you need to replace k by k plus cap n. Does anything change? No. Therefore x of k plus cap n equals x of k. So this immediately tells you, you need to be worried about x of k only for what values of k? 0 to n minus 1, because x of cap x of k is periodic with period cap n, therefore you need to worry about cap x of k only for k values in the range 0 to n minus 1. So this is one immediate fallout of this. So now this person who was so kind to give you the definition of the DFT, alright, was also kind enough to give you the inverse DFT. So this person then says, okay, I gave you the DFT definition, I will not leave you in the lurch, I will also give you the inverse DFT definition, and hence this definition turns out to be k going from 0 to n minus 1 e to the j 2 pi k n by cap n. So, this was the DFT, and this is the definition of the inverse DFT. Then this person to whom this definition was given immediately observed this. What about x of n plus cap n? That is, here now you are going to replace n by n plus cap n. You will get back x of n. Therefore, when we started off this DFT by saying no assumptions about x of n is made about x of 0 to n minus 1, in the DFT framework there is no escaping the fact that x of n is really periodic. So, that is x of n is periodic with period cap n. Therefore, just to summarize, we have x of k is x of n e to the minus j 2 pi k n by cap n, sum up over n going from 0 to n minus 1, and x of n is 1 over n sum up over k going from 0 to n minus 1 x of k e to the j 2 pi k n by cap n. So, these are the DFT and the IDFT relationship. By the way, x of k is called as the kth DFT coefficient, and sometimes this is also called as the kth bin, bin, kth bin, kth coefficient or kth bin. So, k is also called as the bin index, standard term used in the literature. So, one thing that is clear is, given a sequence which has n values, so n point sequence gives you a transform that is also n points. N point sequence gives you n point transform. Now, we can immediately see that this DFT, which was not the name to any of the 4 Fourier series representations that we had seen so far, and when I had started that, before giving what the definition was, I told you it could be the potentially the 5th representation, turns out to be nothing but the discrete time Fourier series. Recall that AK, the Fourier series coefficient, was given by this, k going from 0 to, rather n going from 0 to n minus 1, x of n e to the minus j 2 pi k n by cap n. This was the Fourier series definition. N times AK is nothing but n going from 0 to n minus 1 x of n e to the minus j 2 pi k n by cap n. This was nothing but x of k. Therefore, the DFT is not the 5th Fourier representation, but it is nothing but the discrete time Fourier series with a slight change in definition. Again, everything is consistent, because in the DFT framework, even though you start off by saying no assumption is made about the data outside the observation window 0 to n minus 1, the DFT framework immediately produces periodicity. The sequence in the DFT framework is periodic because x of little n is the same as x of little n plus cap n. The Fourier series coefficients are also periodic because cap x of k and cap x of k plus cap n is the same, they are the same. Therefore, the sequence is periodic, the transform is periodic. In fact, the famous Cooley-Tukey paper 1965, which talks about the fast Fourier transform or FFT, which we are going to discuss after we are done with the DFT and its properties. That paper's title was an algorithm for machine computation. They did not say FFT or DFT. An algorithm for machine computation of complex Fourier series was the title of that very famous paper. That also brings up this point. So, all the Fourier series representations that we have seen so far could not be represented on a machine except this, which is the DFT. DFT is the same as DTFS, which is slight modification, right. So, continuous time Fourier series, the signal is independent variable is continuous, no good for machine representation. The Fourier series quotients are infinite in number, even though they are discrete, no good. Continuous time Fourier transform, both the signal and the transform are in general infinite in duration. Not only that, independent variable is continuous. DTFT is nothing but CTFS in disguise, again no good for machine representation. Whereas, look at this, the sequence is periodic with period cap n, therefore you have to deal only with n independent samples, finite number, good for machine representation. Transform, the DFT coefficients are only n in number, therefore n point signal produce n point transform, that also can be represented on a machine. The only thing that you will have to worry about is quantization, because you do not have infinite precision, but then throwing as many bits as needed you can control quantization, and for all practical purposes you can, at least in the first course, you need not worry about quantization effects. Therefore, of all the Fourier representations we have seen so far, the only one that is amenable for machine implementation and machine computation is the DFT or the DTFS. DTFS and the DFT are synonymous, alright. So, no other representation can be implemented on a computer. Okay, your question.
But there are time sequences also like finite, right? We considering it will be periodic after that.
Yes.
It may not be.
Yeah. So, again this is a very good question you are asking. You should have asked this question when Fourier series was taught to you, continuous time Fourier series, right. So, there you are assuming a signal to be periodic, x of t plus cap t is the same as x of t. There also it is of infinite duration. The fact that it was independent variables continuous is one part, but the infinite duration part you still had to deal with it, right. So, no signal is of infinite duration, right. So, that objection also, the one that you raise in this context, you should have raised in that context as well, correct. Yes. No, but your objection was to the fact that this is of infinite duration, and you said that there is no signal that has infinite duration, correct. So, your objection to this was from that angle, not from the storage point of view. But again, you should have asked this question when Fourier series was taught to you. No signal has infinite duration, right. The universe itself is supposedly only 15 billion years old. Earth is 4 billion years old or something like that. So, no signal could have begun before the universe was created, as physicists tell us. So, yet we deal with signals that start at minus infinity. So, what gives? So, what is the use of those representations then? Okay, it helps in mathematics, so okay, it helps, surely it does. So, how is it used? How does it help you? Here, you're using this for a practical application, correct?
The signal which we are interested in much smaller as compared to the code.
Okay.
Infinite is relative.
alright. Oh, infinite is relative, okay, as far as engineers are concerned, right, you should not be saying this to the math people. So, okay, so the point that you are making is, yeah, very good. So, basically these things help you to kind of have a conceptual framework that in which you can bring the ideal signals and not worry about the approximation that you are making. Just like an impulse is a very good approximation for a short duration pulse. So, all transients would have died down when you turn on the function generator and apply it to a circuit. Quickly the transients will die down, and then you will observe the steady state response, and that circuit is best analyzed using steady state theory, thinking of infinite duration sinusoids that were switched infinitely long ago. So, these are models that are used in practice to approximate actual workings.